Welcome again. We'll now get into more detail on what Typhoon is, what it is used for, and what the goal is of this project. So it was a collaborative project between these four artists. It's developed at Ghent University by a Maritime Technology Division. We're going to talk about the goal, why do we use it, what do we intend to use it for, then get into a little bit of a background on the theory which is used for. So firstly, of course, the dynamic stability and assessment, which is really important. And later on, we'll also talk about the Vortex Lattice method. This Vortex Lattice method is the way how we calculate force and moment derivatives used for the dynamic stability analysis. This Vortex Lattice method is nothing more than a way to perform this dynamic stability analysis. We could also substitute this, for example, for computational fluid dynamics, but it has some drawbacks, as computational fluid dynamics has a higher cost, is more accurate, of course. In an early design stage, this Vortex Lattice method is therefore more interesting, and it's why we incorporated it into Typhoon. And last, we will, of course, also talk about Typhoon, what we can do with it, how we intend to use it. So Typhoon, the main purpose is to quantify stability, is to perform this dynamic stability assessment. And why do we want to quantify this? It's a way to compare different designs in an early design stage from a stability standpoint, that we really get an idea about the dynamic characteristics of this design. Therefore, we should be able to define a geometry. Well, we want to compare different designs, so we need to be able to define different geometry, of course. We also want to define conditions, higher speeds, lower speeds, other elevations, trim angles, you name it. We all need to be able to define this. And lastly, Typhoon should also be able to calculate forces and moments, as it needs to be able to calculate forces and moment derivatives. Now some theoretical background. What is a dynamic stability analysis and where does it come from? So to reiterate, dynamic stability assessment is a way to quantify stability, to really get a number on stability and about the dynamic behavior of the hydrofoil craft. It all starts from the 12 equations of motions. So you got 6 dynamic equations where you get your forces, force balance, your moment balance, and 6 kinematic equations. In these 6 kinematic equations, it's nothing more than, for example, the time derivative of your speed is an acceleration. Quite basic. If you would get all these equations of motion together, they contain 12 motion variables, which are listed on the right in the state vector, and forces and moments. In the state vectors, you have position variables, you've got angle variables, you got your speeds, and you got your angular speeds. If we now assume a small disturbance around a static equilibrium, then every motion variable and every force and moment will be disturbed. This static equilibrium is put in bold. Why? Because it's really important that we start from a situation where the hydrofoil craft is said to be in equilibrium. So all forces and all moment balances are resolved. So now there is this small disturbance and every motion variable, every force and every moment is disturbed. So we can substitute these terms for their disturbed value. So every motion variable, for example, the elevation, is substituted for its static equilibrium value plus a disturbance value. For the forces and moment, it is not as straightforward, as they are a function of the flow field and therefore cannot be directly substituted and written out in these disturbances because we don't know them. They are a function of the flow field. And that is why we substitute them for a first order Taylor approximation, where we have delta x, delta a, which is a force derivative, times this disturbance value, delta, big delta, AI. And this AI is for every motion variable, the 12 motion variables in the state vector, which I mentioned on the previous slide. So every force and every moment gets substituted for 12 distinct force derivatives multiplied with the disturbance value, as it is listed there. The result we get then is the entire system of equations of motion, these 12 equations of motion, can be rewritten as a time derivative of the state vector is A times this state vector. And this matrix A is called a stability matrix. And this is where actually everything is all about. If we would assume the entire system of 12 equations, it would look something like this. I won't get into too much detail why some terms are written with a dot and some with a star. That's for other papers. But this is how it then all looks, and this is what the stability matrix is. If we now assume only a symmetric boat and longitudinal motions, we can use a reduced stability matrix or a longitudinal stability matrix. And then it gets the following outlook. So again, a reduced state vector, a time derivative of it is equal to A times this same state vector. And this matrix A, again, a stability matrix, the reduced stability matrix, and it gets the outlook which you see on the right. And in this stability matrix, we recognize mass, we recognize mass, moment of inertia, and these are terms we know about our design. But we also get all these force and moment derivatives, and these force and moment derivatives are needed to evaluate the stability matrix. Why do we need to evaluate the stability matrix? It's because we need the eigenmodes of this matrix to determine the dynamic behavior and to quantify stability. So these forces and moment derivatives need to be calculated somehow. And that is why we use the Vortex lattice. That is why we use Typhoon. So Typhoon uses the Vortex lattice method to calculate forces and moments. It's a potential flow theory where we can superpose different aspects about the flow. Again, I won't get into too much detail about how this is. It's just to give you general background and why we need to use it. Again, we need this Vortex lattice method to calculate forces, to calculate drags, to calculate moments, and so on. These are the more theoretical, mathematical background to it. It's a system where every panel, so every foil of the hydrofoil craft gets iterated into different panels, and every panel has something which is called a horseshoe vortex and a collocation point. And every horseshoe vortex creates circulation, and a collocation point is a point where there is a Dirichlet boundary condition where you just say that it can't be any flow in the normal direction. This way, this panel is said to be impregnable, and therefore we got a closed system. Then this is what is used in the typical softwares, typical codes used for airplanes, but this is not enough for a hydrofoil craft because we also need to use the free surface. And therefore, we got also a wave module. It's a more difficult mathematically and conceptually. So again, I won't get into too much detail, but this way, this is needed to get a speed dependency and also to get a submersion dependency. So we get a lift which depends on one hand on submergence below the free surface, but also on the speed. Okay, now we need to get in more detail about what Typhoon does. The first thing which Typhoon is able to do is calculate the static equilibrium. I accentuated this a couple of slides ago that we performed this dynamic stability assessment in a static equilibrium, but we don't know the static equilibrium in a certain condition because it depends on every condition, but also not for every design because it also depends on the design. So we need to recalculate this every time. And Typhoon is equipped with an algorithm which is suited to find the static equilibrium. So in this longitudinal case, to find z force and also to find the moment around y-axis to stabilize the craft in a longitudinal way and how to find where it is in this static equilibrium. So it changes its trim, it changes elevation, and then it finds its static equilibrium. So that's the first thing we need to do. Then we can calculate in this point these force derivatives, these moment derivatives, and we can find a stability matrix. Once we have a stability matrix, it's nothing more than calculating eigenmodes and therefore eigenvalues and eigenvectors of this stability matrix. This is some example of a hydrophobic catamaran. It had two complex conjugated pairs, one real eigenvalue, and if you would plot all these eigenvalues in a complex field, then we get the plot which is shown below. What can we now conclude out of this is that all these eigenvalues have a negative real part. Why is this important? This tells us that the system is dynamically stable because every disturbance would get dampened out over time and would again converge to the original static equilibrium position, which is very important for a dynamic system. The other thing which we also can see that we have a real eigenvalue, but also two complex conjugated pairs. Complex eigenvalues always exist in pairs, and they will lead to an oscillating motion which would gradually dampen out. A real eigenvalue will lead to an exponentially decreasing, in the case of a negative real part, in an exponentially decreasing motion towards the end. So now, if we look at the eigenvectors assigned to each of these eigenvalues, for example, for the first and second eigenvalue, which is lambda 1, lambda 2, this negative real part, a complex conjugated pair, we see in the eigenvector, which is plotted below, that it's a coupling motion between either the pitch and the heave motion. So it will lead to some kind of wobbling motion, which is heavily damped. Why? Because it's very negative as a real part. So it will be damped out quite quickly. The third and fourth eigenvalue also complex conjugated pair. And again, a coupling between heave and pitch, so some kind of wobbling motion, but very much less negative, still negative, but it will be lesser damped, and therefore, where the first and second eigenvalue would dampen out quite quickly, the third and fourth will lead to a very gradually decreasing eigenvalue. And again, this coupling between heave and pitch. Then the fifth eigenvalue it was real eigenvalue, so it's exponentially decreasing, and it's a coupling between the forward speed and the draft. And it's something which we expect if suddenly there would be a small disturbance which increases the speed of the vessel. Then we will expect more lift, and therefore the craft will have a lesser draft. This was a short introduction about what Typhoon does and where it is used for, and some theoretical background. The next few tutorial videos will be more into detail about how to use the software and also interpreting the results.